Earth never fails to surprise us. Just when we think we've nailed down how plate tectonics work, we stumble upon seismic data indicating possible sunken plates buried in regions where no known boundaries exist. These bizarre formations lurk below the western Pacific and parts of South America, turning the standard geologic map on its head. As if that weren't enough, researchers on Easter Island found rocks hundreds of millions of years older than the oceanic crust they rest on. A revelation that challenges the long-accepted idea that oceanic plates and hotspots behave like a neat conveyor belt. So, what's going on beneath our feet? Are these plates the fossilized remains of long-lost tectonic slabs? Or are they something entirely different? Meanwhile, Easter Island's ancient minerals spark debates about just how persistent hotspots can be. The evidence suggests that at least one mantle plume might have stayed in nearly the same location for a mind-boggling 165 million years or more. If that's true, then our traditional models of an ever-churning mantle may be missing a key piece of the puzzle. By digging into these mysteries, we're forced to confront just how much of Earth's interior is still uncharted territory, despite centuries of scientific inquiry. From sunken plates that shouldn't exist to magmatic plumes older than the dinosaurs, we're about to explore revelations that may forever change how we look at our planet's inner workings. For decades, scientists relied on a narrow method to map Earth's interior. Traditional seismic imaging typically used a single wave type, often P waves, which provided only partial snapshots of the mantle and core. This was like trying to read an entire book by only glancing at a few select paragraphs. While this approach yielded plenty of insights, it also left major gaps in our knowledge. The introduction of full waveform inversion changed that landscape. This method integrates every available seismic signal, P waves, S waves, surface waves, and more, to build a three-dimensional map of the planet's interior. Processing these colossal datasets is no small feat. Researchers needed cutting-edge supercomputers to crunch the numbers. Yet once they did, the payoff was immediate. They saw not only the expected subduction zones and mantle plumes, but also perplexing new structures that look startlingly like tectonic slabs in places where they shouldn't be. At first, there was skepticism. Some geologists suspected data errors or artifacts in the wave simulations. Repeated checks, however, confirmed that the anomalies were real. These newly revealed regions stood out because their wave speed profiles resembled those of subducted oceanic crust, commonly known as slab graveyards, yet appeared far away from any modern or known ancient subduction boundary. The results suggested a hidden complexity in Earth's mantle that scientists had never clearly observed before, turning what should have been a refined picture of well-understood processes into a massive puzzle. Subduction zones are typically found at known boundaries where tectonic plates collide. The denser of the two plates, often oceanic, dives beneath the other, creating trenches, volcanic arcs, and regular seismic activity. Over millions of years, that subducted slab descends into the mantle, where it eventually loses its identity through partial melting, mineral transformations, or slow stirring by convection currents. That's why discovering plate-like formations hundreds or thousands of kilometers from any recognized subduction zone is so unsettling. One hypothesis is that these slabs date back to a much earlier time, perhaps when the supercontinent Pangaea ruled the globe. Back then, Earth's geography was drastically different. Tectonic boundaries might have snaked across regions that are now oceans or deep beneath continents. If these slabs formed during an ancient subduction event, they could have drifted or sunk into the mantle, staying surprisingly intact for hundreds of millions of years. Another explanation posits that these anomalies only mimic sunken slabs on seismic scans. Different mineral assemblages, varying temperatures, or anomalies in density can all generate wave speed signatures that look slab-like. A region of iron-rich mantle or a zone that has undergone repeated melting could, in principle, give off a false plate imprint when interpreted through seismic data. Yet the structures are so large, consistent, and layered in ways strongly associated with subducted crust that many scientists suspect at least some of them really are leftover slabs. If proven correct, these slabs raise fundamental questions about how long subducted plates can remain coherent and how Earth's interior might preserve ancient tectonic artifacts. While full waveform inversion offers an unprecedented look into the planet's depths, it's still not an absolute truth machine. Seismic waves show us variations in speed, but these shifts can arise from multiple causes: temperature gradients, changes in composition, the presence of partial melt, or even small amounts of water in minerals like olivine. Interpreting wave speed data is a little like reading coded signals. Multiple keys might decode the message, and different geologic scenarios can produce similar wave signatures. As a result, some experts remain cautious. They argue we need complementary evidence, such as gravity measurements, electromagnetic surveys, or deep drilling data, to confirm the true nature of these puzzling anomalies. Others are calling for more sophisticated computational models that factor in not just wave speeds but also realistic mineral physics. Only by combining different lines of evidence, they contend, can we make a definitive call on whether these structures truly are primordial slabs or simply zones of dense, chemically distinct mantle rock. Yet few geologists doubt that something unusual is down there. The repeated detection of these plate-like features across multiple datasets and depths underscores that they're not likely to be mere illusions. They appear robust and far-reaching, enough to force us to confront the idea that Earth's interior might contain a tapestry of old, dislocated slabs, kept intact by a mantle that's more complex than our standard models suggest. While scientists grappled with these deep-sea enigmas, a separate bombshell discovery unfolded on Easter Island, best known for its towering Moai statues. On the island, researchers collected lava samples containing zircon minerals, tiny crystals that act like time capsules. By measuring uranium-to-lead ratios, geologists accurately pinned the zircon ages at roughly 165 million years old, a figure that clashes starkly with the 2.5 million year age of the island's own volcanoes and its underlying oceanic crust. How is that possible? Oceanic crust younger than 200 million years is standard. Older seafloor segments are typically subducted and recycled back into the mantle. Yet here were zircons from a realm when dinosaurs thrived, embedded in lava flows that formed relatively recently. The most plausible explanation ties to mantle plumes, columns of hot, buoyant material rising from Earth's deeper layers. If a plume under Easter Island taps into an ancient pocket of mantle, it could bring up zircon crystals formed long ago. However, the real shock is the plume's apparent longevity. Conventional theory says these plumes can be long-lived, but 165 million years pushes the envelope even by generous estimates. If the same plume has continuously supplied magma to evolving oceanic crust for that span of time, then Earth's mantle circulation might be more sluggish, or at least more uneven, than the conventional conveyor belt model suggests. Textbooks often depict Earth's mantle as a uniform system of convection currents, with hot material rising, cooling near the surface, and then sinking back into the depths. Tectonic plates ride these currents, colliding, splitting, and subducting in a dance that recycles crustal material over hundreds of millions of years. But the anomalies under the Pacific and the data from Easter Island suggest this dance may have secret steps. If subducted slabs can remain relatively intact in bizarre locations, and if plumes can stay anchored for 165 million years or more, then we may be dealing with a patchwork mantle that moves at different speeds. Some areas might be as dynamic as we've always believed, churning, mixing, and pulling plates along, while others could remain almost frozen in place. These immobile zones could trap ancient slabs or preserve mineral signatures that date back to the early days of the planet. They may even function like vaults, keeping geological records that would otherwise vanish in the mantle's gradual churn. This refined view could also explain why volcanic hotspots like Hawaii or Iceland persist in roughly the same location for so long. If certain portions of the mantle hardly move, then the plumes originating there can keep feeding magma to the surface at the same coordinates, creating island chains and volcanic plateaus over tens of millions of years. Easter Island's super-ancient zircons become less baffling in such a scenario, though they still cast doubt on how quickly or uniformly we think the mantle flows. These developments spark deep questions about Earth's past and future. If plate-like remnants linger far below, could they still influence surface processes? It's possible that these ghostly slabs, through slow chemical or thermal exchanges, might affect the timing and intensity of volcanism or even trigger earthquakes in areas we deem stable. The existence of ancient plumes also raises intriguing possibilities for how volcanic provinces form. Perhaps many of Earth's large igneous provinces, such as the Deccan Traps or the Siberian Traps, were fed by superplumes that endured far longer than we believed. From a resource standpoint, discovering more about deep subduction remnants may alter where we look for valuable minerals and elements. Some precious metals and rare earth elements concentrate in regions of intense magmatic or hydrothermal activity. If the mantle's geometry is more nuanced, geological prospecting might follow new patterns, especially near ancient or reactivated plumes. Comparative planetology also comes into play. If Earth's interior is so much more complicated than we assumed, what about Mars or Venus? Mars lacks active plate tectonics, yet might harbor ancient plume signatures beneath its dormant volcanoes. Venus has no visible plate boundaries, but could contain relic slabs. Studying Earth's anomalies could provide a template for interpreting data from other planetary bodies, shedding light on how common or rare tectonic recycling might be in the cosmos. Naturally, not everyone agrees on how to interpret these anomalies. Some geoscientists believe the slab-like features might result from temperature variations that mimic the velocity signatures of subducted plates. Others point to potential errors in data processing, although repeated checks seem to minimize that possibility. The Easter Island findings also provoke lively debate about mantle dynamics, with some insisting that 165 million years is within the realm of possibility for a stationary plume, and others suggesting that an as-yet undiscovered phenomenon must be at work. Regardless of which camp one falls into, the quest for clarity is already driving new initiatives. Seismometer networks are being expanded worldwide, especially on the ocean floor, where data coverage has historically been poor. Researchers are refining full waveform inversion to process noise and subtle signals that earlier algorithms dismissed. They're also exploring non-seismic methods, like measuring gravity anomalies or magnetotelluric data, which capture the electrical conductivity of rocks, a property that can hint at composition and temperature. In the lab, scientists are recreating extreme mantle conditions, subjecting minerals to crushing pressures and scorching temperatures. By testing how real minerals react, melt, and change at various depths, they aim to match those properties with the seismic signals we observe. If we can narrow down the specific wave speed patterns associated with basaltic crust, iron-rich accumulations, or dehydrated mantle, we'll get closer to deciding whether the hidden plates are genuine slabs or some exotic geologic formation. As with any emerging concept, skepticism abounds. It took nearly half a century for plate tectonics to gain broad acceptance, once viewed as a radical idea. Now it's the bedrock of Earth science. We may be seeing a similar shift. The notion of immovable mantle plumes and ancient slabs might feel like a radical leap, but evidence keeps mounting that our planet's interior is far from a uniform, continuously mixing mass. If these ideas gain traction, we may need to rewrite major sections of geological textbooks. Imagine an Earth in which large volumes of deeply subducted crust can hang around for eons. Some slabs might fuse with ancient mantle reservoirs that stayed put since the planet's formation, maintaining a distinct chemical fingerprint. The Easter Island plume, or others like it, might have been pumping magma into oceanic crust for longer than 165 million years, possibly explaining not just the island's odd zircon ages, but also other geological anomalies scattered across the Pacific. In the grand scheme, these puzzles highlight how much we still have to learn about the planet beneath our feet. We often talk about exploring space, but Earth's mantle remains an equally mysterious frontier. Layer by layer, we're discovering that the interior could harbor complex interactions, subduction ghosts, plume vaults, and labyrinthine structures that defy simple convection models. In the end, these discoveries serve as a powerful reminder that Earth remains a living, evolving puzzle. The potential existence of sunken plates in places they shouldn't be upends the neat boundaries and timelines we've come to rely on. Meanwhile, Easter Island's ancient zircon strongly suggests that at least one mantle plume defied the supposed rules of planetary convection, persisting in place for far longer than expected. If both findings hold up to future scrutiny, the conventional picture of a uniformly churning mantle, driving plates in predictable cycles, will need serious refinement. Such a revision wouldn't be merely academic. It could shift how we assess seismic risks in areas once thought tectonically safe. It might also reshape our understanding of volcanism, resource distribution, and the conditions that make Earth habitable. And it may inspire a new generation of scientists to probe the deep mantle more aggressively, harnessing advanced seismic networks, lab experiments, and computational models that push the boundaries of what we can simulate. Ultimately, the lesson here is one of humility. For all our satellites, drilling projects, and sophisticated imaging techniques, the Earth still guards many of its deepest secrets. Every time we peel back one layer of the planet's interior, we uncover new complexities that force us to revisit and often dismantle our cherished theories. But that's the essence of science, a never-ending quest to see the world, and beneath it, more clearly, guided by each astonishing discovery. As we continue exploring, It's safe to say this won't be the last time our planet surprises us with something seemingly impossible, only to reveal how much more we have yet to learn. Thanks for watching. Please like and subscribe if you enjoyed the video, and I'll see you on the next one.